So I'll talk about this Indian genius Ramanujan. So you see nowadays also if you go to the Max Planck in Germany, so they try to there is a Ramanujan as a notebook, okay, and they try to translate and try to see what are the hidden gems in that notebook, okay. Okay, कहाँ तक है? ये दिखाई दे रहा है? Okay, so it was a hidden gem in Ramanujan's notebook. So there are something that's still being unearthed. So basically, they try to see that what is the new modern counterpoint of that. So today I'm going to talk about something that Ramanujan never thought of. It will come out this way. So talking about 1910. So he was looking at something very partition functions, and this is the functions. Most of you know. The number of ways n can be partitioned. Okay, so he was looking at this nice thing, and of course, all of you know if you take P1, so there is only one, there is one. If you take P2, this is 2. This is because 2 equals to 1 plus 1, and this is equals to 2. This is thing, and then P3 is 3. This is because 3 equals to 1 plus 1 plus 2 plus 2. This is equals to 3, and so on. So he wanted to see the natural numbers. The numbers, the main problem is that they are infinite. So he wanted to see that can you see how these partition functions are, can you say if here P1, P2, P3, you can very easily say, but the numbers are, there's a main problem is that numbers are infinite. So if you take P100 and it's P100 you can say, but it's very huge numbers. Can you see a pattern on that? So what you have to do is that you look at, so he looked at, you see all of them, you can look at it as a power series. So 1 plus x plus x squared. 1 plus x squared, 6 to the 4. What I'm looking at this is like a power, this is like a no power, this is like a square. So this power series we can do it. So this is, all of them you can write it as this is like a thing, and this coefficient, so generating coefficient for every natural number, even if n is million, this Pn you can write down. Okay, so that is what this Ramanujan starting for this power series you can talk about even to the high school thing, this power series, and you want to ask what is this Pn. So Pn is the generating functions of this. Okay, so what you do is that, so of course from the high school you know that this 1 plus x squared, this is 1 minus x, and this 1 plus x squared, this is 1 x squared, this is 1 minus x cube, all of them this is equals to sum is to 1, sorry, this is equals to plus Pn x to the power n. Okay. And you want information about this 1 minus x squared like this. So this is what Ramanujan's delta function is. So Ramanujan's delta function. So you want information about this Pn, and what you do is that this delta x, you look at, this is equals to x times 24. So he wrote down this power series. This power series you can write down, and this power series is going to give you information about this Pn. Okay, and this is what is known as Ramanujan's delta function. And you know now this story that they said like people do not, they said that some goddess gifted her, what are the coefficients? You like this is like a harmless power series, but they said like some goddess gifted her with this coefficient. He wrote down this like coefficients of this power series. So how to this one? So this delta x, this is equals to tau n x to the power n. And he wrote down this for this tau, these coefficients, he wrote down using this. So then you have this n, I'm writing down these n's. Yeah, this is what 3, 4, 6, 7. So these tau n's, I write down these tau n's. This tau n is 1, 24, 252. This 1472, 830, 6048. So this is what he said, like God has gifted her with this number. So what you see, there is no pattern in these numbers. Okay, there is something. Okay, so but there is a pattern to it. Now with we live in 2024. So I am going to write down this. Just any natural numbers. You can write down this sigma k of n. This is sum over dn d to the power. So this is certain functions associated to natural numbers. You take all the kth power. You are counting, so all the kth power. Let's see, I just write down this sigma 11 n here. Now, so is this the definition of the sigma k n is fine? You are just, for every natural numbers, you are just adding the k minus 1th power of that. And then I just sigma 11n, I'm writing down. You see, this is 1 plus 2, 11. And this is your 1 plus 3 times 11. This is 1 plus 11. 11 and plus 2 to the power 11. 2 to the power 11. Yeah. Okay, so so Ramanujan thought about, of course, he said like God gifted her, God gifted him this 691, and this is like nobody knows like how he got this that time. So tau n minus sigma 11 of n by 691. If you look at this, this is of course 0. This is 3. This is 256. This is 6075. 7656 52300. Okay, so today's talk, I would like to see why Ramanujan talked about this 69. What is so special about this prime 691, and how you can get something more generally than 691. You see, that time there was like, it is, I'm talking about 1920, before that, I think Ramanujan died in 1917, right? So after 20-30 years, Hecke, he is a German mathematician, he invented what I'm going to define, what is called modular forms. But you see, there is a pattern, you see, there is a multiplicating. Tau n has certain things, he wrote down, this is like a power series. This power series you can write down. You can this thing. He wrote down certain properties of this function, these multiplicative functions. Okay, he read down very nicely, and after 30 years, Hecke just started from this delta x and defined what I'm going to define, this modular forms, and this all the properties he wrote down here, that becomes properties of the modular forms. Okay, yeah, you have any questions? Okay, so I will just today's talk, I'm just trying to see what is this 691 is all about. So how do you get much more general objects like 691? So what is after this thing? You see, this is like this is generally things. Tau n is congruent to say modulo 691. Okay, so he got here, and this, by the way, 691 is a prime. Okay, 691 is a prime, and what he got is that all this tau n that is wrote down as a partition functions using this like this coefficient, and these functions you can write down very easily. For natural numbers, you can write down what are all those sums, right? So even if you give 1 million, you can write down what is this sigma kn, right? Modulo 691, there is always a prime. So that will come to it, because this is delta function is going to modular from weight 12. And this sigma 11n is like, this is only one, there is only one Eisenstein, something I'm going to define Eisenstein series, and there is only one Eisenstein series. So this is one dimensional, and this modulo 691, there is one dimensional space. So this becomes a modulo 691, this is the modular forms. Okay, that's why it is one dimension. Yeah. So Ramanujan did not think about, so is God gifted with this natural congruences. God is gifted her. So it's like him, but it is actually now we live in 2002, almost 2024 over. So we know how we got it. Okay. So I'm going to define what is the modular forms. Okay, this is. You see, Ramanujan was looking at this power series, and now with the advance of science and maths, so we know how to do it in a more this modular forms. Okay, forms. So this delta x, this is what is known as modular forms, one modular forms, and this sigma kn, this is going to give you one modular forms, and this is a congruence between two modular forms. Okay, so you have this upper half plane. So this is the H, this is your Z, Z belongs to C, imaginary part of Z greater than 0. So modular forms are one functions from upper half plane to C, and two, you have this, you see this upper half plane, you have a nice group. What is the advantage of this upper half plane? This is subset, I want to see it as subset of C. And what is the advantage is that your discrete, certain discrete group, namely SL2Z acts on the upper half plane. Okay, and I demand f of AZ plus B plus D equals to plus D to the power minus K f of Z. So if this definition looks quite, this first time if you see it looks quite weird, but basically we are looking at this is like a upper half plane and it's like a Riemannian manifold, it's a Riemannian curvature -1, and what you are looking at the differential forms on this Riemannian manifold. Okay, and 3, f, very importantly, f is holomorphic at infinity. So this is what Ramanujan's thing. So what is the meaning of this infinity? So that's what people say, that he can see infinity. So this, all this like power series expansion, what he got is that it is getting at the infinity. You have this upper half plane, and then you have a functions. All of you know that there is a function z goes to e to the power twice pi I z. This will take you to the unit ball. This is your q mod q less than 1. So I told you this function is a holomorphic. This function is a holomorphic. That just means that from the complex analysis, this just means that around each point you have a power series expansion. You take a point, around this point you have a power series expansion. Yeah, and but that is not guaranteed if you are at the point infinity. You see. You have this upper half plane, you have this function, very nice function, z goes to e to the power twice pi I z. Upper half plane under this function will take you to the unit ball, namely q mod q less than 1. But what will happen to the infinity? Infinity means it's very far away point, this is I infinity. Okay, infinity will go to the point 0 here. Huh. Yeah. So I just, okay, let me just, this basically FQ, DQ, tensor K, this is holomorphic. So one of them is, I think it's minus K, no? FZ, it's going, it should be K. Okay, fine, yeah. So, yeah, sure. Thanks, sir. Yeah, the other side, yeah. So basically, this function fq dq tensor k, this is going to be holomorphic and this invariant. This is very important. There is SL2Z invariant under this plane. Okay. So you have this z goes to e to the power twice pi I z. You have this I infinity and this very far away point. It is not guaranteed at the point 0. Okay. And if this holomorphic at infinity means at the point 0 also, it is like holomorphic. So holomorphic means complex analysis will tell you it has a power series expansion, and that power series expansion will give you that power series that he wrote down there, right? So this is the meaning of, so every modular forms is given by certain power series like this. Okay, let me just write. So this is, if is holomorphic, it just means that GQ holomorphic on H So if you take this function GQ, f of log Q by twice pi I, this is holomorphic on D minus 0. And this just, okay, so and this you can ask that why this function is well defined, because 2 will tell you that this is f is holomorphic, if satisfied, it is invariant under this property. So in particular it is what is periodic functions, f of z plus 1 equals to fz. So this function GQ is well defined. Okay, so this is now a well defined functions on this nice plane, and I demand it to be f to be holomorphic at D. You are cutting off this 0, and I demand it a G is holomorphic at 0. F is holomorphic at A, G is holomorphic at 0. At 0. This is the definition of f is holomorphic at infinity, and that is what one you can see infinity. Yeah. So if you have f is holomorphic like this, so what will happen is that it has a power series expansion. So once you have a function which is like a from upper half plane, yeah. Yeah, sure.
So what is holomorphic?
Holomorphic means it has a power series in the sense of this, like a, holomorphic means like a power series expansion. You have complex analysis, right? Complex analysis. It just means the Cauchy shows this Cauchy-Riemann equation. Cauchy-Riemann equation should be satisfied. So you have this complex plane, right? So you have complex plane around each point. You can write it as a power series, a n z power n. So that is the, so this is like a so it satisfies. So I mean, I would like to see it like a Cauchy-Riemann equations, because like most of the time if you go to the dimension higher, so then this power series expansion will not work. So but it satisfy a function should satisfy Cauchy-Riemann equations. Okay, so del z of f and del z bar of the f equals to 0. Yeah. So this is a function the complex, and I would like to see it as a function of the complex analysis. Yeah. Yeah, so you have, so what will have that if Z has a power series expansion. So take home message is that any modular forms has a power series expansion. So similar to analytic, huh? So this is like an analytic. You can write down. You see, any functions you can have this like negative terms are also there. So I demand it that, that's my demand is that you do not have any negative terms like 1 by z term should not be there, right? That is a problematic for me, right? I want real power series. So that's why you see these are this like partition for this real power series, like 1 by z terms should not be there. 1 by z square terms should not be there. All the negative terms I don't allow. We are just working with the positive terms. Yes, that is what. Okay, Ramanujan, that time there was no powers that, whatever I am defining, I am 2024 is like this modular form, it came in 1940 or something. That time he didn't know about this upper half plane all. He was just looking at this power series, okay? And he wrote down this congruences he wrote down. It's not before that, okay? So he just...
more interestingly, like those toys, I mean, not more interestingly, interestingly, I should say. So, as Professor mentioned, these are multiplicative, which means if you take 2 and 3,
yeah, so
if 2 and 3 is 1, then you can also get 6, because you just multiply negative, like 29 and 252. So 29 multiplied by 252 if you do, and you look at the 6th column, you'll get 6048. These are also multiplicative, as long as GCD are close to
you just have to look at the prime. You say natural number, every natural number can product of prime numbers. You just have to look at the prime. And that just lots of work has been reduced, right? So if you know for prime 2, you know for prime 3, you know for prime 6. You don't have to do any new work. So you know for prime 3, you know prime 5, you know 15. Okay, so that is the advantage. Yeah. Yeah, that's a corresponding. Yeah, all the corresponding.
and then you can do the mod of that, right? If you do the mod and mod of
that
another relation, which is
this
Ramanujan conjecture, and
v to the power.
Yeah, exactly.
So P to the power 11.
11 by 2. 11 comes from, again, modular form.
He also wrote down this. He wrote down this one, and this is very important. Thanks for thinking. And he didn't know, but there's like goddess gifted her this. Like,
And that was 1970s.
90 some French mathematician, he got it, but that's got a Fields Medal.
Very hard to, not easy, very, very hard to. And Ramanujan didn't know all of these, right? No complex analysis.
So what did he base on?
So he,
God is gifted, right? So
basically, Mike wrote down the series. It was like genius of highest order. Maybe.
genius.
The patterns.
Yeah, that's a pattern. Just looking at, you see like power.
But the thing is that what he started with, this became very important, right? This has so many modern, even with physics, there are connections.
Yeah, this nowadays.
Excel model, Max's,
Sorry, because
Yeah, sure. That's okay. Yeah.
so but I'm able to appreciate the beauty of it and perhaps I've missed it. So how is this delta function you're talking about it in a very plain language different from a usual delta function that we
Delta function means what?
Dirac delta function.
yeah, something like that.
No, that's totally different. Nothing to do with that. There's small delta. This is capital delta. Deductive. Yeah, this is nothing to do with it. This is totally no connection.
This is Ramanujan's
This is okay. So I should Ramanujan's. It's Ramanujan's.
different words.
They did.
And it finds some really applications.
Yeah, physics out loud nowadays. Physics, yeah. There is a symmetry. You see, this like is capturing the symmetry. What I'm saying is that here there is a certain. You see, so here. What you say, if you know for 2, 3, you know for 6, okay? So if you just know for prime, so here if you know for some of them, it's like basically modular forms, if you know it for 1, 1, 0, 1, what is the value, then you know a lot of things. So there is certain symmetries there, and that is being captured by other people, right? So these values, okay, so this you don't need to know the value. The SL2Z is generated by S. There's 2 nice matrices, and these values, if you know, you know the lot. So basically, there is you must have seen this like. So there's ICM. There is a thing. So if you just know about this, okay. So if you know this value here, you know the value everywhere. So that is the advantage. There's symmetries. There's a supersymmetries and all, right? So that is being. Even this prime, there is not here prime. Yeah, but that is related to delta. So you have to write 7. You can write down, right? So 7. What are the numbers of it? But generally, yeah. So numbers. You have to write down the numbers of P can be 7 can be written. 7 equals to 7. 1 plus 6, 2 plus 5. That's way.
I'm talking about this table. You have listed all the values of
Yeah. So here.
That expression, right? Like
it is
just
derived,
multiply it out.
no, it is just derived by hand, right?
Yeah.
That of course you can do, but that is how it is decided.
Ramanujan did that.
Ramanujan that way
Now
too.
we know that this is a modular form, right? This is a modular form of width square.
Yeah. So
Now we know a lot of properties come from the general theory for us, but for Ramanujan,
Ramanujan did it using just bare. He has a notebook. That's what.
I don't know. I mean, no one knows probably.
I mean, nowadays also people are thinking in Germany with how he got those formula. There are lots of papers. I mean, there is written out.
It is there and one can find out term by term.
Yeah. That's what Ramanujan did this that way only. But now that we live in, so now 2024 and all, right? There are certain technologies. So we try to use.
The question is like, why would anyone write expression like that? Like if you change it, if you make 25, then it doesn't work. If you make 23, it doesn't work. 24. Why would one, just write down and,
That's like.
just explore those objects, which turns out to be modular forms of it. That's why
Yeah.
very important.
That time we didn't know, right? What is a model? No one knew what
why
it is.
he explored those.
And that they say like God is gifted. Yeah. So okay. After this, I hope that you know that this modular forms. The advantage is that it is given by a power series. If you replace this q by x, you are going to get that power series. So modular forms are given by that infinity. That person who can see infinity just means that it's like you have a power series, and power series is coming at infinity. Okay, so I will give you one example, namely most this how he got this like sigma kn. That time he didn't know that this is like after 40 years, I think Eisenstein. So this is Eisenstein, he was a German mathematician, Eisenstein series. So I'll give it, this is first example, so we can write down this is GKZ equals to, this is like a, you have to, this is like a z plus d to the power k, so this is CD belongs to Z2 minus 0. Z is a set of all integers including 0. So I demand this. So this is like a power series and it has, okay, so if you have seen it from the analysis course, you have a convergence issue. So for this safety, I take this k greater or equals to 4. In particular, k equals to 12 is allowed. Okay. So this, the Weierstrass M test is going to tell you, M test will tell you that this GKZ is holomorphic on upper half plane, and you can write down this like, so you can ask what is the, you see this is like infinity, you need to see that we are more interested in what will happen to the infinity, and if you write down this, what will be the at the infinity. And I just plug in infinity, and what you are going to see is that I am just writing down this GK of I infinity. For me, infinity is I infinity. So this is 1 by n to the power k, and most of you have seen this. This is just zeta function. Okay, this is twice of, no, sorry, you have to put 2 here because n can be negative, positive, anything. 2 times zeta k. Okay, so this constant terms of that is like this constant terms of this is going to give you zeta function, Riemann zeta function. Zeta is a Riemann zeta function. Zeta function. Okay, so why? So this is an example of a modular forms. In particular, this that will satisfy all the properties I wrote down. So why this is true? If you see that SL2Z is a nice group. This is a group of symmetries. So SL2Z is generated by 2 nice symmetries, namely translation and dilation. So translation means, like the English word translation is 1101. It just take any complex numbers to Z plus 1. Okay, and S is this matrix 0, this 1 1 0, and this is Z goes to minus 1 by Z. You see, this is called dilation. This is translation and dilation. That's why this like the useful thing about modular forms. So I have just drawn here. So it translate, if you look at this picture, so here you have, you translate it here, Z plus 1, you know, if you have information here, you have information here, if you have information here, you have information here. Dilation, what it does is something smaller, it just goes here. Yeah? So what you look at this, if you look at this series, look at this GKZ, I'm trying to show that this function is nice enough functions. So what you do is that, I'm just erasing this. Okay, so it is easy to, if you just GK, this is a, say GKZ plus 1, this is your GK of Z, and if you just plug in here GK of minus 1 by Z, you just plug in there, you just minus 1 by Z, you just this plug in here. So what you are going to get is the Z to the power K GK of Z. So these two properties are satisfied. So if you want to show this function is invariant under SL2Z, not invariant, this corresponding differential forms is invariant, what you need to check that these two, but it's easy to see, and this one, this implies that GKZ is a modular forms. All this property wrote down there is satisfied, and you have to write down this infinite expansion, GKZ equals to twice zeta k plus 2 times minus twice pi I k minus 1 factorial minus 1 n. In particular, if you take G12, this is going to be sigma 11. That is what there is Ramanujan's sigma 11. Okay. So this is an example. This is Eisenstein series. This is an examples of modular forms. Okay, so this is one example, and what is this delta function? Delta function I already defined. So delta function is summation over n tau n x to the power n. So the way I wrote down, it is going to tell you, if you start with the modular forms of weight k and modular forms of weight l, f dot g, it is going to give you modular forms of weight k plus l. Okay, so now this delta z is basically suitably normalized. There is all these problems with this, and this is delta z I wrote down. This is liquid G4 cube, and this is going to be weight 12 modular forms. Okay, and this is going to give you weight 12, and there is what he wrote down here in this congruences. There is a weight and this constant terms. If you just look at, this is 0 because I started with n greater or equals to 1. Okay, and this 12, this G12, if you look at this G12, this coefficient is, I wrote down this G12, this is your E of Z, this is your 691 times 2730 times 624 plus summation n greater or equals to 1. And sigma k minus 1 sigma 11 of n u to the power n. So that is why he got this 691, because it is a constant terms of the Eisenstein series, and delta xz is going to give you this like 0. Yeah. So the question is that, can you have something similar to this 691? So can you have this 691, he got it, but is there any, so what today's thing is that, what I told you is that there is a weight 12, there is only one modular forms, and the constant terms of the modular form, in the numerator of that there is 691, and that's why you have this congruences modulo 691. Okay, so this is what Ramanujan discovered, that we recovered in 2000 this afterwards. Okay. Yeah, the question is that, can you have similar to this kind of congruences for other modular forms? So that is what I did with my collaborator. So what you do is that, what you have here, I define modular forms for SL2Z, but there are some modular forms for congruent subgroups. Okay, so I defined what is this congruent subgroups. Why this upper half plane? If you see points on the upper half plane, it is going to give you elliptic curves. Namely, if you take a point on the upper half plane tau, this is going to give you C modulo lambda tau. Okay, so this is an elliptic curves. Elliptic curves means torus. Okay, elliptic curves is like a torus. It's like a S1 cross S1. Okay, so I want information from not only for elliptic curves but cyclic subgroups. Okay, and for that, this cyclic, you need to go beyond SL2Z. Namely, I will define subgroups. Gamma naught of n, this is your A, B, C, D, C is congruent to 0 mod n, SL2Z. And if you look at gamma naught of n modulo upper half plane, this is going to give you information about the elliptic curve with a cyclic subgroup of order n. So we are interested in the similar kind of congruences, and I will just write down certain congruences similar to that, and I justified it. Why there is a congruence like this? I take this n to be (121) So this is why you're asking that n equals to 121, because the prime level, it is known before us. A person called Barry Mazur, he already found congruences similar to the prime level, and we are interested in prime square level. And then you have looked at this E phi z. This is equals to phi n summation d dividing n d q to the power n. Now this is a modular from the Eisenstein series of level 121. So I wrote down this delta, these are all modular form level 1. So I look at this modular form, so level 121, and you look at this fz equals to, this is, if you are, this is your S2, this is 21, and we found there are congruences, there is a modulo 121. This is one example, and there are several examples. So we went to find out what was the, how he got these congruences, and the issue is that so I'll just write down this theorem. This is this theorem to me and my collaborator and Majumdar. So if n is any natural number, and this order of this Cn of m, this is of course to order of T mod m. M is the maximal idea. Eisenstein maximal. So I'm going to define what is this object, and Cn, okay, so this Cn is the object that corresponds to the infinity for natural number n. Okay, so you have this, I already defined this y naught of n. This is your y naught of n, and this is a Riemann surface. So it's a complex, you have this group, you have to take n greater or equals to 4. If you take n greater or equals to 4, then this group gamma naught of n acts freely and discretely on this upper half plane, and this is a Riemann surface, but it is not compact. So you compactify by adding cusps. This is like a one, similar to 1-point compactification. So you have this y naught of n union this gamma naught of n modulo q union infinity. So infinity is our object. We want to understand. So after this talk, I hope you understand that there is, Ramanujan has some information about this infinity, and this is what we need, that gives you the congruence like 691. So this is going to give you this x naught of n, this is a compactification, and this is a compact Riemann surface. This x naught of n compact Riemann surface. So I wrote down these cuspidal subgroups. This is your Cn. So Cn is the D belongs to this naught of n mod P1Q. This is the definition of the D is fine. You take the point, you see, I am taking this infinity. Infinity is the object at the infinity. Okay, so that's a faraway point. Now I am not looking at this SL2Z, because SL2Z is going to give you level 1. So you want information about the cyclic subgroup of order n. So I have to get information about the gamma naught of n modulo K1Q. In particular, if you take, so that subgroup is Cn. Is it fine? Yeah. So if you look at this, okay, so and I did not define for you what is this object like T. T is this Hecke operator. T is the Hecke algebra. And M is the maximal ideal, and that is the ideal that gives you information about these congruences. Okay, so we know how to compute this Cn of M, and for level 1, of course, it is going to give you 691 at this particular weight, and the other levels also, when I erased it, this level 5 and all, that is how we were getting it. Yeah. Okay, so I think Alok is here. So is this the student? Is it fine? This what? Yeah, so Alok is here, so I'll just talk about a bit about how you can do it for other subgroups. You see, SL2Z is like a first examples of thing. So you can go SL2Z, you can change it to SP4Z. And this SP4Z, there are one parabolic is a Klingen parabolic, and one parabolic is the Siegel parabolic. So I look at this subgroup Kn that Alok has did in his thesis. SP4Z, this is a paramodular groups. This is modular group. And what you can ask that, do you have congruences between this modular form, Eisenstein series and cusp forms? These are the analog of this gamma naught of n, and this is a conjecture due to Harder. I take this n to be prime, and this is the conjecture due to Harder. So there exists f belongs to, this is your Sj k nu kp, such that this Tq of f equals to bq of f. Now, sorry, this is Tq of f, bq of f with bq equals to q to the power k minus 2 plus aq plus j plus k minus 1. Okay, so now you need to tell that what is the this analog of this 691, and the analog of the 691 is the Klingen Eisenstein series. So we have to look at the L prime such that order of L p to the power k minus 1 to k greater than 0. So then there exists a congruences between this BQ and this AQ. So AQ is this Eisenstein series, AQ equals to the power k minus 1 lambda. And if you start with a prime like this, there is a congruences between AQ and BQ. Yeah, so I think this is, I mean, I'm thinking about it with my students, so hopefully I can tell you later. Okay, I'll stop now. If you have questions, you can ask. For here? No, I don't know. So even this one is also new to me. So this one. Okay. So prime power, I can come. This theorem is for any natural number. This is for SL2Z is known. Okay, so this is known for SP4Z, even for this. You see, the main issue that we realize that there is no dimension formula. So you see this SK for classical modular form. These spaces dimension things are not known. So we don't have much information about this. Yeah.
For Ziegler Eisenstein series, is there something?
No, I don't know much about this. Okay, so this is for Klingen things. Okay, that's what I was using your thesis. Okay, that's okay.
Okay, thank you.
Yeah.
Yeah, great talk.
So basically, the take-home message that these congruences are the first baby cases, but there are, you can change this groups. And this is like SP4, you can SP there, you can have new congruences, and that is useful. That's going to use. You see that this function is going to give you information on partition function, but there are other this coefficient. For instance, Siegel modular forms these coefficients give you information how the natural number can be written as product of squares. So that arithmetic functions, you need information on that. So that information is encoded in this Eisenstein series. So that is what Ramanujan taught us. Okay, so.